In this module, we'll talk a bit more about subduction zone metamorphism, pressure-temperature paths that rocks follow within the Earth, and regional and contact metamorphism in collisional tectonics. First, I want to make sure that we're all on the same page with regard to some terminology that relates to describing the chemical and rheological layering within the Earth. And as far as the chemical layering is concerned, we've been using those terms crust, mantle, and core. When we're talking about the crust, we're dealing with the chemistry of the oceanic crust is much like basalt, and the chemistry of the continental crust is like granodiorite or an andesite. Then we've also talked about the mantle being ultramafic, and briefly mentioned the core, but a metallic iron and nickel core. Those three broad zones within the Earth are chemical zonations. So we have different elements present in the crust. There are definitely much more sodium, potassium, aluminum, and silica in the crust, whereas in the mantle it is much more magnesium, iron, and other elements like chromium and nickel. The core we haven't talked really about, but metallic iron and nickel and perhaps silicon, not silica. Those are the chemical layers. Now the rheological layers, those are a physical differences between those layers. So rheology, that term refers to the strength of a rock. And the rheology of the Earth can be broken down into more zones. We have the outermost lithosphere, so litho referring to rock, and spheres that outermost sphere of the Earth. That's a solid, rigid layer of the Earth, and that comprises both the crust and the uppermost part of the mantle. So the lithosphere is more than just the crust. It actually includes some of the mantle beneath the moho, where the mantle is solid and rigid like the crust. Below that, we have the asthenosphere, which is within the mantle, and that's a zone where it's gotten hot enough that it's deforming. It's not rigid and solid like the lithosphere. And that's described as being a plastic layer within the Earth. So we have that weak layer, the asthenosphere, that is underlying the tectonic plates that are moving around on that deforming layer. Beneath that, we have the mesosphere, which is the lowermost part of the mantle beneath the asthenosphere that is solid because of the great pressures getting down deeper into the Earth. The outer core is a liquid outer core, and that is rotating also with the Earth, and that rotation of the liquid outer core is what gives us our magnetosphere and gives us the north and south poles within the Earth. Beneath that is the inner core, and that's a solid inner core. So those different layers on the left-hand side of the diagram, those are all rheological layers, so different strengths of those different layers of the Earth. Whereas on the right-hand side of the diagram, those are chemical layers. And we use both terms, so I just want to make sure that everyone is familiar with all of those terms before we proceed. All right, we looked at this diagram before for subduction zone metamorphism, and I just want to reiterate some things. We're looking at an oceanic continental collision zone, so we have basaltic crust that's being subducted, and the oceanic crust itself is in this light blue color. That is what is metamorphosing to blue schist and eclogite facies. And as that metamorphism is taking place, we have hydrous minerals breaking down during metamorphism, like clays, micas, amphiboles, that all are hydrous, have that hydroxyl pair within their chemical formulas. That structural water is driven off, it's more buoyant, it rises into the mantle wedge, which is lithospheric mantle, right? This is part of the lithosphere, so it's a solid mantle that's underlying that continental crust that we're subducting beneath. When that water enters the solid mantle wedge, that's lowering the melting temperature of the peridotite, if we want to generalize about the chemistry of the mantle. It's lowering the melting temperature of the mantle wedge and generating partial melts that are then buoyantly rising up underneath the crust and generating a volcanic arc. Those magmas that don't actually rise to the surface and are erupted are crystallizing within the continental crust and give us batholiths like the Sierra Nevada batholith. And then I'll point out also the isotherms that are shown on here. The subducting oceanic crust and the lithospheric mantle that's beneath it are being taken down the subduction zone or pushed down the subduction zone, and they're dragging those cool isotherms with them. And it's the pressure within the subducting slab is increasing much faster than the temperature because it's dragging the coolth with it. This is a similar subduction zone diagram that is emphasizing some different things that are going on in terms of metamorphism in the subducting slab as well as the overlying mantle wedge. So if we look at the upper diagram first, you'll see that it is showing you blue schist metamorphism at lower pressures or shallower depths and increasing to eclogite facies metamorphism with increasing pressures. And so we're seeing, as I pointed to before, the amphiboles, the phyllosilicates, and other minerals that contain the water, those hydroxyls, those are being driven off as actual water from the crystal structure, and we're crystallizing instead minerals like pyroxene and garnet. That water is entering the mantle wedge, and now look at the lower diagram. This water that's now in the mantle wedge is causing some metamorphism of the mantle itself. And so at lower pressures, you're seeing the growth of serpentine, talc. At higher pressures and temperatures, amphiboles and phlogopite, which is the magnesian end member of biotite. So we're seeing metamorphism both in the subducting slab itself, as well as the mantle wedge where those fluids have entered. And this example is from Oman. And this is that area where there's that spectacular ophiolite that I showed you pictures from, where it's a complete section of ophiolite that's exposed. But this is looking at the subduction system itself rather than the ophiolite that's overlying. And in this, it's showing again the isotherms that are being dragged down the subduction zone, and the temperatures at which you're seeing the blue schist metamorphism, somewhere between 450 and 550 degrees Celsius, and at higher temperatures, eclogite metamorphism, higher pressures and temperatures. And so that increasing metamorphism is also causing density increases too. The pyroxenes and the garnets are denser than the amphiboles and the micas that are in the blue schists. And what happens is at some point, the subducting slab becomes so dense that it actually breaks off from the oceanic crust that's being subducted, and that piece that breaks off actually drops off into the mantle and is recycled into the mantle. And at that point, that's basically when you start to see the return of some of this subduction zone material to the surface. And so you'll see actually a particle path for an eclogite during a burial and exhumation. It's showing you this line here where it's an eclogite that's part of an oceanic crust that gets subducted, there's slab breakoff, and it returns to the surface basically along that subduction zone. I like this diagram because it gets to the point that it shows not a nice, neat, clean line for that subduction zone. You're actually seeing this messy subducting slab that has areas that are being broken off and start a return path toward the surface. It's showing you that there's sedimentary material as well as oceanic crust, as well as this serpentinized mantle wedge. All of those components are traveling back up the subduction zone in a mixture that we call a melange. And that's exactly what we see in the Franciscan complex around us. And if you go to Ring Mountain and Tiburon, you'll see that there are blocks of the high pressure, low temperature blue schists and eclogites exposed there. And those are mostly sitting, there aren't very many of them, in fact, probably because they're very dense and those tend to get subducted. But they're floating in a matrix. These grassy hillsides are serpentinite. So all this serpentinized mantle wedge is actually helping to bring those high pressure, low temperature rocks back up to the surface. So these rocks are following a prograde metamorphic path as they're being subducted in that subduction zone, where you're seeing an increase in the metamorphic grade as you're increasing the pressures and temperatures moving down the subduction zone. And so we call that prograde metamorphism. And when they come back up to the surface, those rocks are experiencing retrograde metamorphism. And that is where you're seeing a decrease in the metamorphic grade as the rock is being exhumed to the surface and being subjected to overprinting of lower pressure and temperature metamorphism during that exhumation. So the rocks in a subduction, we'll just use the subduction zone as the example now, but you're seeing what looks like a clockwise pressure temperature path where you're seeing the prograde metamorphism as pressure and temperature is increasing, and at some point on that pressure temperature path, you're reaching the maximum pressure conditions for those rocks. And when they return back to the surface, you're actually seeing an increase in the temperature. So after the maximum pressure conditions were reached. And then the retrograde path is what's followed when the rocks are returning to the surface. And in the case of a subduction zone, that's when they're coming back up that subduction interface. So if we're looking at a metamorphic facies diagram that we've seen before, the rocks in the subduction zone are following this high pressure, low temperature PT path up into the eclogite facies, where they reach their highest pressure conditions. And then they're starting their return to the surface, back towards surface conditions, and that's the retrograde path. And on their way there, they're reaching the highest temperature conditions, right here. And so if we just draw a simple PT path, you'll see that they're undergoing the blue schist and the eclogite facies metamorphism on their downward journey. And then perhaps they're falling through amphibolite and green schist facies on the way back to the surface. And that's very common to see amphiboles that aren't glaucophane, but hornblends replacing the omphocytes and eclogite, because they are recording that retrograde metamorphism. Now, if we're talking about regional metamorphism, so we're considering more moderate pressures and temperatures, like the Barovian rocks that we're looking at in class. Those too can have a prograde and retrograde pressure temperature path as they're buried, they're increasing the metamorphic grade, and then they have to return to the surface where we're collecting them so we can study them. So they are also having what looks like a clockwise pressure temperature path that they're following. And that might look very different in terms of what you're seeing in the overprinting relationships with the metamorphic minerals in those rocks. So instead of going through blue schist eclogite facies metamorphism followed by amphibolite and green schist, maybe we're seeing a path that looks like this, where we're going through green schist and amphibolite facies metamorphism, maybe even into granulite facies metamorphism, and we're growing kyanite. And then on the retrograde path, we're moving from that kyanite stability field, we're passing over into sillimanite stability, and we see sillimanite growing after the kyanite on those rocks' return journey to the surface. So we see those kinds of relationships too, and that's quite common to see sillimanite growing after kyanite in regionally metamorphosed rocks. So we discussed the subduction zone metamorphism that's happening actually in the subducting rocks, and oftentimes we're seeing that in oceanic crust that's subducted beneath the edge of a continent. And the regional metamorphism that's taking place where we're folding and faulting and thickening the crust in an origin. And when you're thickening the crust, you're burying rocks more deeply than they have been, than they were before the mountain building began. And that's where you're getting the regional metamorphism. Now that's not taking place right around the plutons. What's happening right around the plutons is the contact metamorphism, the very high temperature and not necessarily high pressure or even moderate pressures, sometimes very low pressure metamorphism taking place. So two kinds of metamorphism are happening in the orogeny, the regional metamorphism and then just the contact metamorphism in those aureoles just right around those plutons. Now, if we look at kind of a model collision system, in this one we have a subduction zone and volcanic arc developing and a passive margin. A passive margin is one where there's no tectonic activity taking place. So there's no subduction zone, there's no arc forming or anything. So that's where we're starting from. And what we see in the forearc is marked by A. There's deformation taking place that we can call a D1 deformation, the first deformation. And there's also deformation taking place within the arc itself, perhaps around the Pluton as it's being in place, and no deformation around C, around on that passive margin. And this deformation that's happening during the mountain building is all going to be accompanying the metamorphism, and we see overprinting relationships with both. Let's progress the origin further until we have the development of a second subduction zone beneath that passive margin. And now the deformation in the original volcanic arc that's outboard of that former passive margin is experiencing a second stage of deformation, a D2 that is overprinting the first deformation. You're seeing folding and thrusting in the forearc. You're seeing the development of deformation in the subduction zone in the new forearc. And then finally, when you have accretion of the volcanic arc to that former passive margin because of the subduction, we're closing that former ocean and accreting an arc to a continent. We're seeing continued deformation in the whole package of rocks, and not only deformation in the former forearcs, but in around the Pluton emplacement, and then of course that the deformation that's taking place within the arc itself that's thickening the crust, and where we're getting regional metamorphism in here in that thickened crust. So all this deformation is taking place at the same time as that we're getting as we're experiencing metamorphic events. We're seeing subduction zone metamorphism in both of those subducting slabs. We're seeing regional metamorphism in the arcs where the crust is thickened. We're seeing contact metamorphism right around Plutons. And it's all taking place at the same time as this deformation is taking place. So we're seeing lots of overprinting relationships. And when we get to talking about metamorphic textures, you'll see that metamorphism and deformation go hand in hand. So if we evolve that system to the present day, and we've eroded or perhaps scraped off by glacial processes the tops of that origin, what you're left with are the former accretionary prisms. You're left with those rocks that were in the arc with the regional metamorphism. You're left with contact metamorphism around the Plutons. And what's not represented here actually are any ophiolites that might take place, that might be emplaced between the accretionary prism and the former arc. And we're not seeing any high pressure, low temperature rocks being exhumed there. But that's where we would look to find them. Now, if we consider the origins around the world, where you're going to see the metamorphism that we've been talking about, both in the subduction zone, the regional metamorphism, and contact metamorphism, you're looking to places that in geologic history have undergone these collisional processes. In North America, we have most of Alaska is comprised of these accreted terrains. We have the Franciscan in the western U.S. The same thing is taking place or took place along western South America. We're seeing that in the Alpine and Himalayan systems across South Asia and southern Europe. And there are more ancient mountain belts, and we've talked a little bit about the Appalachians and how those are related to eastern Greenland and Norway. There are more ancient, the Paleozoic origins in the Urals. There are Mesozoic mountain belts in eastern China. So in all of those places, and of course very new arcs down in Indonesia and Malaysia. These are all places where we're going to see those kinds of rocks, along with ophiolites. Okay, so what you learned in this module was that subduction zone metamorphism is a high pressure, low temperature kind of metamorphism, that metamorphic rocks follow a pressure temperature path, and those rocks can record prograde and retrograde metamorphism, and as well as deformation. That exhumation of the high pressure rocks takes place within a subduction zone. That regional and contact metamorphism are both taking place in collisional tectonics, where we have a thickened package of crust and plutons being emplaced all at the same time. And then we're getting multiple metamorphic and deformational events that are ending up with overprinting older events. And it can get quite complex. So the next module will deal with metamorphic textures, and we'll see some of this deformation and how you can relate different stages of metamorphism, different stages of deformation in what you're seeing in the rocks.